Good evening, everybody. And it's our great pleasure to have Professor Christina Rousselle today and to give us a webinar. Thank you very much. Please allow me to introduce Professor Christina Rousselle briefly. She is a professor at the University of New Orleans. Her main research fields are fundamental combustion to applications and new combustion models, low and zero carbon fuels such as ammonia. This is what she will talk about today. And she has held positions at the International Energy Agency, which is the IEA, as representative of France, and as co-chair of the IEA Clean and Efficient Combustion Technical Collaborative Program. She is a fellow of the Combustion Institute, associate editor of the Proceedings of the Combustion Institute, and the Journal of Ammonia Energy. She was chair of the second symposium on ammonia energy held at the University of Orléans last year. She has also chaired the mini symposium about ammonia spray in the International Conference of Numerical Combustion. Thank you very much, and let's welcome Professor Christina Rousselle.
Thank you so much for this nice introduction, and thank you also so much for inviting me to give this lecture about ammonia, which is my molecule that I love for the moment, because I'm convinced that we have so many things to do, not only for technical point of view, but also for research. So we try to convince you that ammonia could be a beautiful fuel for internal combustion engine, but also I think we have to remind always that ammonia and hydrogen is the same things. What I want to say, it is the same economy in order to have a clean and we hope new future planet. So as you know, in Europe, we try to change our mind in order to use a lot renewable energy, but this could be done only, in fact, we can storage them. So when we talk about renewable energy, it could be solar, wind, geo, hydro, bio, tide, and also in France, because I'm French, it will be a little bit nuclear ones. So all of you certainly know that chemical storage is very benefit, because in the chemical species, we have high energy densities. And from that, we can produce through the water electrolysis or some other process that it needs still to be developed. We can produce hydrogen or other alternative fuel that we call usually e-fuels, and ammonia is one of them. So the idea after, sure, from ammonia, we can retrieve the hydrogen contents and use ammonia only as an energy, as an hydrogen carrier. But our objective from combustion community is to use ammonia itself as a fuel. It could be in gas turbine, in boiler on furnaces, internal combustion engine, and there is also some development in order to use ammonia directly in some solid fuel cells. Okay. The use of ammonia as fuel for engine is in fact an old story. So first we will start with a small joke. It was the first ammonia engine developed by French engineer de Laporte during the 19th centuries. But as you can see, there is no combustion. It's only due to the change of phase between liquid and vapor and the increase of the pressure to produce energy from this thermodynamic machine. So what happened from the past? In fact, there was several projects on ammonia thermal engine from the last 90 years, mainly mixed with reactive fuel. It could be gasoline, diesel, biofuel, DME, methanol. And one famous, in fact, story, it's about the Belgian buses company during the Second War, where they filled, in fact, their engine with a mixture of ammonia and cold gases, so synthetic gas. They run more than 10,000 miles, but sure, you can imagine it was a long time ago, so we have no real idea about efficiency, no real idea about pollutant emissions. So we have to wait until 2010, more or less, when we have a pickup developed by the Michigan University, where they filled their car with a mix between ammonia and gasoline. Between these two dates, in fact, there was a lot of study during the 60s done by the US laboratory and also the Department of Energy in order to know how it's possible to use ammonia as fuel. After that, there is another example, very famous in Korea, with Amvec cars. It was also ammonia gasoline or ammonia diesel, it depends. And at the same time, there is one first Toyota car developed, Marangoni Toyota. And more recently, there is some other, in fact, initiative like the Hydrofuel Incorporation to use ammonia for automotive. But until now, we don't know exactly what it is done. So anyway, if we look on the road, there is no vehicles with ammonia until now. What's the problem? Safety, emissions, combustions. I hope that we will learn more after this presentation. There are some other applications to use thermal engines. It could be genset, it could be auxiliary power unit, off-road vehicles for construction, for mining, for ports, some cranes, and so on. This will be very valuable. There is a two projects that I know for the moment about the use of ammonia itself as a fuel for tractor. This could be very local solution, very interesting, because we can imagine that we can use ammonia as fertilizer and also ammonia as fuel. Okay, what are the global ammonia combustion characteristics? They are not so good, sure, especially if we look at the heat energy in millijoule per kilogram of fuel is very small in comparison to what we can get with hydrogen or gasoline. But due to the small stoichiometric air-fuel ratio, in fact, if we consider for the engine application by kilogram of air, we can see that the energy that we can have in the input could be really similar to what we can get with gasoline. About the research octane number, we can see that it is very high, with also a high auto-ignition temperature. So it's good because, in fact, this will limit the knock occurrence, even if we use high compression ratio, high turbocharging conditions. But the high auto-ignition temperature induces that it will be very difficult to use ammonia in compression ignition engines. We can see also that the adiabatic flame temperature is slightly 200 degrees Celsius lower than hydrogen itself. This is good because we will decrease the thermal NOx, but what's happened about the fuel NOx itself? And last, most of people talk about the laminar burning velocity problem that we can have with ammonia, as it is very small, 7 centimeters per second in comparison to 40 centimeters per second that we can get for hydrocarbons. How can we improve this flame speed? Do we need to improve it? Okay, so it's clear that there is no appropriate combustion properties for piston engine. So how can we use it as fuel? In fact, there is a lot of challenge to obtain very clean and efficient ammonia engine. As we see, it is difficult to ignite, so this will have a strong impact on cold start. It's a big issue, we can say that, but it is an important issue when we have a vehicle on the roads. So we need ignition strategy, promoter, pre-chamber ignition. There is a narrow flammability limit, so perhaps we will have some more problem with the stability operating conditions. I told about slow flame propagation, so this it will be quite the similar impact. And also what's about the fuel bound nitrogen, what will be the consequence on pollutant emissions. Okay, if we look on from the past, so from the study done, in fact, during the 60s, It was based on the theoretical analysis with this combustion parameter, and also some tests in the CFR engine, so research engine. So the main conclusions are drawn here. So sure, as I already told you, due to the low stoichiometric air-fuel ratio, we will increase strongly the fuel consumption. This we cannot do without this consequence. So it could be about 2.5 increase in comparison to gasoline one. It seems that from the study that it is possible to run at low equivalence ratio, but sure, due to the small flame speed, we need to advance a lot the spark timing. And also, it could be also a problem as function of the compression ratio. So what could be the solution for ignition? Different type of igniter, ignition promoter like hydrogen additions. Globally, they try to increase the compression ratio to enhance the combustion, and what it is a good result. With the increase of the compression ratio, we can increase the combustion efficiency as function of a different engine speed. If we increase the intake pressure, we also increase the global efficiency, and better efficiency can obtain in comparison to gasoline itself. Okay, but why we are so interesting on ammonia engine now? In fact, in 2019, the International Maritime Organization did their first strategy in order to decarbonize, in fact, the maritime sector. So the target is clear in 2050 to be as close as possible to 0% of CO2 emissions. This means that, in fact, they have to change their fuel. And there are different studies on different perspectives. What will be the future maritime fuel in 2015? There is a kind of one scenario, and what we can see, ammonia will be one candidate. It is not so easy because until now, there are not so many. There is a lot of ammonia, but it is for fertilizer. So first, we need to provide more ammonia. And also, as you know, the way to produce ammonia is not until now very green. But anyway, it will be for the future. So certainly no before 2030 or 2040, we will have ammonia as fuel for marine engine. It is an example of provided by Man Energy Solution in one conference, when we can see that in the future in our sea, in fact, we have different fuels as function of the ships, as function of the travels, as function of their functions themselves. So if we look what's happened now about marine engine development, there are different announcements. The first one was from Fartila with a 2 and 4 stroke project. Another one, it's WinGD to convert to methanol on ammonia itself. MAN already developed 2-stroke ammonia engine, and they work also in 4-stroke. And more recently, HI power system in Asia to provide, they succeed, in fact, to do ammonia diesel engine with 20% of diesel content. If we look on the website, there's a lot of announcements. It's clear that ammonia will be the fuel for the future, and this will be a revolution. But we have also some new example about some tests that it will be done in Germany in order to power trains with ammonia. And also, certainly, you know that there is a recent announcement that GAC will provide on the road also the first ammonia car engine, and this was also announced by Toyota itself, that our new ammonia engine will bankrupt the entire EV industry. So we never know what will happen, but this is very positive for ammonia economy. Okay, So from the past on until now, there is different way to try to initiate and to have an ammonia engine. Most of the time, we mix with something. But if we want to fully decarbonize and to limit the carbon footprint, there is no way. We need at least biofuel like bioalcohol, biomethane, biodiesel, DME, or, as it could be easy, hydrogen. But perhaps we can also run engine with pure ammonia. So we look until now for the global combustion parameters, but what about the emission energy? It is a recent study where they try to measure the emission of ammonia, nitrogen, ammonia, hydrogen mixture. So here it's 100% of ammonia, and they add some contents of hydrogen. We can see that sure, as we increase hydrogen, in fact, there is no issue. We can increase a lot the minimum emission energy that we need between 100 millijoule to 1 millijoule. So the difference is so big with only 20% of hydrogen. If we look on the laminar flame speed, sorry, I don't know why, but it doesn't work. Okay. Oh, yes, it's okay. So we can improve this flame speed by adding some other fuel like methane or hydrogen. But what's happened in engine, in fact? In engine, what we can see here, so it's for one bar, 3 bar, and 5 bar, and there is for 400K, 500K. As you know, in fact, the laminar flame speed is function of temperature and pressure. And what we can see, in fact, this coefficient for the temperature dependence and pressure dependence are not similar to what we can have for hydrocarbons. The dependence in temperature is higher and the pressure dependence is lower. So the consequence is, in fact, in engine, as we have high temperature and high pressure, it could be totally different than what you can have with hydrocarbons. And also, from another study, what we can see that when we increase the compression ratio, so when we simulate, in fact, the laminar flame speed at the ignition timing, we can see that even for compression ratio about around 10, in fact, the laminar flame speed is strongly enhanced. And we are not so far, finally, to what we can get with methane. With hydrogen addition, sure, it's an easy way, perhaps, to promote ammonia if we consider that we can bring around the engine a small cracker to partially cracked ammonia to provide the right additions of hydrogen that we need to ignite and to improve, in fact, the laminar flame speed. It is the solution that adopt, in fact, Toyota to develop their engines. We can see here with 30% in volume of hydrogen, we reach similar laminar flame speed than methane. Another parameter that could be interesting, it's about the quenching distance, which will change the flame wall interaction, and this can affect also, sure, the heat losses at the wall. We can see it's a recent paper when they calculate the quenching distance for different equivalence ratio on different additions of hydrogen, 20%, 40%, 100, in comparison to pure ammonia on different pressure. Here I put an example of iso-octane quenching distance as function of the equivalence ratio. And sure, we can see that around the stoichiometry is more or less 2 millimeters of quenching distance. And if I try to see what is exactly the same for ammonia, finally is not so far. It's a little bit lower, but not so far. But in comparison to hydrogen, it will be a very big difference, especially when we will have, in fact, the effect of pressure. Because with ammonia, what it is interesting when we are between 0.8 until the stoichiometry, there is no big, in fact, effect of pressure in comparison to what we can get with some other fuel. So, in fact, anyway, the quenching distance is big in comparison to hydrogen, is a little bit higher than with isooctane. What's about the thermal efficiency? Unburned species, radical, and temperature gradient will induce also N2O emissions. So the question remains, what are the best facilities to use ammonia? When I consider 95% of ammonia, no 80%, no 60%, no 70%, this it works. We know that we can do it. But when we want to really consider ammonia engine, we have different ways to do it. We can use ammonia in gaseous or liquid phase, pod fuel injection, direct injection of or mix of both. We can add onboard cracker to add a small quantity of hydrogen on how we will inject hydrogen itself. We can use a spark ignition engine, combustion ignition engine, but as I already told you, it will be difficult to auto-ignite ammonia, so therefore we need to add a reactive fuel with a pilot injection. What about the load? The load as function of the RPM, because we have different type of vehicle between marine ships and between car. The RPM will be very different. We have some trouble about cold start. We have a trouble about ammonia NOx trade-off. So, sorry, I already told you, so I will change. So what's about the impact of engine architecture for ammonia engine? So our objective first was to do some assessment about combustion ignition, stability, efficiency, and pollutant for poor ammonia as well as possible. The idea was to identify the minimum of hydrogen that it needs, in fact, to have a very good engine. We did also some other study in order to see what's about the possibilities to use other fuel like ethanol, methanol. And we focus also on cold start conditions as function of low speed, low load, and to see what will be the effect of compression ratio, piston chamber design, diesel type versus spark ignition engine, identify the limit on trade-off NOx versus NH3, and also to try to have an idea about the global warming impact through the N2O emissions, as the global warming impact of N2O is 300 times this of CO2. And we look also the possibility to ignite ammonia with a diesel pilot, and we will see that in fact we can ignite until very lean occurrence ratio, 0.2 of occurrence ratio of ammonia air premixture, with the lowest diesel charge below 5% in energy. So first for that we use a GDI engine. We changed nothing, and the compression ratio was only 10.5. We don't change the piston geometry. We don't change the compression ratio itself. We use the current igniter also. And what we did, in fact, we did a fully premixture between ammonia and air, or ammonia, hydrogen, air, through the intake planob on an heater. Okay, first, it is very interesting to see that, in fact, as function of the intake pressure, we can run ammonia, pure ammonia. It was possible even at atmospheric pressure. There is no real difference in IMP with or without hydrogen. And the maximum work was obtained slightly rich conditions, 1.05. And if we look on the example at 1.1, 1.2 bar of intake pressure, we can see that we obtain similar IMP that we can get with CH4. Okay, this is quite similar, but it is a map as function of the quantity of hydrogen that we can have for different intake pressure. And sure, we can verify that always slightly rich condition seems to be better to get mean effective pressure maximum. But so Also, when we increase the intake pressure by 20%, it's interesting to see that, in fact, we will increase the IMP by 22%. So sure, it's better with the turbocharger conditions. About the indicating efficiency, what we can see, unfortunately, the maximum is not when we are slightly rich, but when we are slightly lean. And we can see that the efficiency is more or less between 35 and we can get until 38%. So it's really comparable to what we can have with conventional fuels. What about, in fact, the emissions? Here we have the emissions of unburned ammonia. Here we have the emission of NOx. They are plotted on function of the occurrence ratio. This is the point that we can have for 100% of ammonia, where we can see that sure we have a lot of exhaust emissions, it seems. And when we add 5% of hydrogen, so 5% of hydrogen, as expected, when we decrease, in fact, the occurrence ratio, we decrease unburned ammonia. But even if we are in lean mixture, we can see that the unburned ammonia quantity remains important, about 1%. And about the NOx, it is the opposite. The NOx increase with the decrease of the occurrence ratio. When we add more hydrogen, we decrease strongly ammonia emissions, but we increase strongly also NOx emissions. So, in fact, we have a small emission window, like, for example, here, between 0.71, where perhaps we can get the optimized ratio between NOx and ammonia. What I want to say, most of engine manufacturers, they thought that they will put SCR, selective catalytic reactor, or selective non-catalytic reactor, at the exhaust for the problem of NOx. But for that, we deal ammonia. And if we use the unburned ammonia, we still to be sure that we have the right ratio, the optimized ratio between NOx and NH3. So this is an example where we said, yes, we can do it, and it is the optimized. About N2O, we can see that, in fact, N2O remains always below 100 ppm, but and also decrease with the occurrence ratio. But even 50 ppm, it's too much if we consider the global warming impact. So I think that we have no choice. We need development of after-treatment solution. And it will really different than what we can get with conventional fuel operating conditions. Okay. We had hydrogen. We see with hydrogen what we can do. But what's happened, in fact, if we use a compression ignition engine, we add a spark plug because the idea is to use the higher compression ratio. It will be better for ignition, better for flame propagation. And also we can consider that it is less expensive in cost because we will retrofit current diesel engine. But as you know, the main difference between spark ignition engine and diesel engine will be that there is no turbulence, only a strong swirl motion. And what's happened in this case for unburned ammonia? So first, we compare between both, in fact, engine. So they are more or less similar. The unique difference is compression ratio on the combustion chamber itself. So this is for spark ignition engine. What we already see is when we decrease the occurrence ratio, we decrease a little bit the IMP. So it is for non-atmospheric intake pressure, so it's for low load. And what it is interesting, when I add hydrogen, I can go to lower load, so to reach cold start conditions. But they are limited. And we can see here, even if I add more hydrogen, I cannot go to lower load, and the effect of equivalence ratio remains not so significant. When I increase the compression ratio by changing the engine, I can reach very low load conditions. So this is very good for cars or trucks. It's a good improvement of ammonia combustion with compression ratio increase despite of the flow field. No hydrogen is needed. I can start the engine straight away with ammonia itself, and we can extend the low load limit until 1.7 bar AMP, as in fact Toyota did 2 years ago with a reformer. And there is also a good low load conditions with low RPM. So it remains a little bit strange to see what's happened in this kind of engine due to the flow field itself. And if we look on the flame, we can see that we have a beautiful, in fact, a weakened premixed turbulent flame. There is no two-phase as we can have when we put a spark-assisted diesel engine with gasoline. It's only premixed flame propagation. There is no difference between the spark ignition engine and the spark-assisted diesel one. So what's happened? How the combustion could be fully premixed propagation without turbulence? So we try to see what happened because we have higher, in fact, higher compression ratio. So the conditions at the spark timing are a little bit increased as in terms of pressure and temperature. But the consequence on the laminar flame speed at the ignition delay, it's in fact, it remains similar to only 2% of hydrogen. This cannot explain, in fact, easily what's happened or why it is better. But if we look more or less on the development of the turbulent flame in the case of ammonia, in fact, turbulent flame of ammonia are more wrinkled than what we can get with a methane flame or hydrogen flame. And when we go with a diesel engine, in fact, we go here, so we come back to the corrugated flamelet, and this is not the case when we use previously our spark ignition engine, where we were more or less near the broken reaction zone. About the unburn, unfortunately, to use a diesel type engine increase a lot the unburned ammonia due to the screech zone. And we can have until 2%, until 4% of unburned ammonia. It's totally unacceptable. What it is also interesting, when we are the stoichiometric or slightly rich, we have also hydrogen emissions. And this is important, even many people doesn't consider that, because what we can do with this hydrogen in the exhaust port. So we try to improve ammonia combustion. We can improve it by change the ignition igniter itself. And this was nice because with highly performant, efficient igniter, we can, in fact, we don't need to go to this high compression ratio, and we can get lowest IMP that we can get with 4% of hydrogen at high engine speed. So it's an advantage. But also how we can do something in order to decrease the unburned ammonia. So for that, we did a study with Aramco by changing the shape of the piston ball. So in yellow, it's the baseline one, conventional diesel reentrant piston ball. In red, it's low quench ball. So in order to favor, in fact, the flame propagation and to avoid the screech zone on the flame quenching, or also another one to the blue one, okay, to minimize, in fact, the heat losses in this area. Okay, here it's the fuel consumption, some specific flame propagation duration, like the ignition, total combustion development of first part of combustion development or total combustion development. It's totally incredible because against what we expected, the baseline piston report the best in fact, fuel consumption. So in fact, it is not better even if we change these shapes. And also the blue one report an advance, but not a lot. And what it is more important, it's the advance beginning of, so it's advance beginning of the combustion with this shape. So what we expected, less in fact quenching of the flame. So anyway, between this shape and the blue one, it's more or less similar. So it seems that removing, in fact, this part don't have a significant role. So they did some CFD modeling with Converge in order to see what's happened. And we try to look on the turbulent kinetics energy, which is in fact significantly higher with this type of piston shape. Okay, so this is just above on the ball and in the squeeze zone, which is has a lot of impact for unburned ammonia. So in this case, for the squeeze zone, sure, as expected, due to the shape of the piston, we have lower TKI. If we look on the flame development model with the SAGE calculation, with the Krishna-Shweta mechanism, what we can see, it's in fact the flame kernel grows and propagates in the above ball region, on the ball region, when there is a higher, in fact, TKE. The blue ball shape has a higher swirl ratio, okay, but this is not good, in fact, because we have larger convective heat losses. And this counterbalance, in fact, the increase of TKE due to this shape. If we look also at the end, so when we are in fact in the squeeze zone, what we can see that in fact 10 degrees after top dead center, the flame enters the squeeze zone, and when we are in this shape, so it means with a less flame quenching. Okay, so if we look on the code flow simulation, it's clear that from both simulation, from both type of ball, we can see that we have a reversed or not screech motion. So the conclusion, it's a geometry that promotes higher TKI in the piston ball, enables to accelerate the beginning, so the beginning of the combustion, the first phase, but a geometry that reduces TKI via a lower reverse screech flow in the screech area slow down the combustion. And this high risk, so in fact, high reverse screech flow is needed for ammonia combustion. And this is really different than what we expected. Anyway, I told you that high compression ratio are very good. So what's about knock occurrence? First, if we look on the ignition delay for 40 bar and 50 bar that we measure recently, for pure ammonia here or for ammonia plus 5% of hydrogen, it's clear that there is a big gap between these two fuels. Okay, there is no issue, it's a big gap. So certainly we expected more knock occurrence in the case of small additions of hydrogen than in pure ammonia. So we did some experiment with a relatively small compression ratio. It's only 14 at 1000 RPM, medium load. On what we can see, we have knock, sure, but we have never knock with 100% of ammonia. We have some knock with 5% of hydrogen and more occurrence with 10% of hydrogen. So this is an idea of about the knock frequency that we can get. So here it's a 1 bar of intake pressure. We increase the intake pressure and we can obtain knock. But to predict NOx, the question remains what about emission delay prediction through kinetics mechanism. So we test 40 kinetics mechanism. For different equivalence ratio, we measure, in fact, emission delay at different pressure from 40 bar until 70 bar. And also we have some things relatively difficult to understand until now. When we increase the equivalence ratio, we have some strong discrepancies on individual, in fact, emission delay that we cannot explain. So this is perhaps a limit of ammonia instabilities. This will be presenting in the next symposium of combustion. Before to conclude, I want to show you some comparison that we have done between spark ignition and pilot reactive fuel ignition with the same engine at 60.4 or compression ratio. So we don't change the Bosch injector, the common line injector. And we try to minimum the diesel content by optimum the engine stability. The injection pressure was 200 bar. And for the spark ignition comparison, in fact, we try to set the ignition timing in order to have the same CA50. So first, what it is interesting, this is the minimum of diesel energy fraction that we need to ignite ammonia engine with 60.4 of compression ratio. And we can see that we could be below 2.5 of energy share by diesel content until equivalence ratio of 0.4. So it's relatively very good because we don't need a lot of diesel energy content. And we can ignite until equivalence ratio of 0.25. So it's really lower than the flammability limit. And it is very lower equivalence ratio limit that we can get with a spark ignition engine. In spark ignition, we cannot go below 0.75. Okay. About the indicated power, sure, there are some small difference because there is the energy content. So this is not so important, but what we obtain it's not only due to the diesel fraction, because the diesel fraction remains, it's only 2.5%. Okay, so it's not due to that. It's also mainly due to the better combustion efficiency. And we have also longer combustion duration with a spark ignition. And so there is a strong enhancement of the combustion itself with the diesel ignition. Not really by the turbulent spray, because don't forget that it is only 200 bar, so it's very low injection pressure. This the turbulent motion and entirement of the air has to be relatively low. So it's really due to local, in fact, mixture fraction between non-reactive and reactive, so like RCCI engines. So the last important question, what's about the emission for ammonia engine? Combustion exhaust gases from ammonia fuel engine will include NH3, NOx, N2O, as I already told you. And this is true. It's the triangle for ammonia combustion, the risk triangle. NH3, it's about safety problem. NOx, it's about health. And N2O, it will be the impact on the climate. So about the premixed ammonia in spark ignition engine, we can draw something like that. So as function of the equivalence ratio in the other side, we know that we will have unburned ammonia in rich zone and certainly hydrogen, like we can have CO in hydrocarbon engines. And in the lean side, we will have NOx, but NOx with ammonia is not exactly at the same equivalence ratio. The peak is not at the same equivalence ratio that what we can get with the ammonia engine in comparison to gasoline one. Moreover, the minimum for unburned ammonia remains function of the engine design, as I show you. And also, we have to consider hydrogen emission itself due to the in situ cracking of ammonia. Minimum for each mixture, maximum about 0.7, 0.8 of occurrence ratio for NOx. It could be until 5,000 ppm, so this is really important. And unfortunately, NOx emission will increase the hydrogen additions. What's about when we ignite with a decane, so with a diesel content? In fact, NH3 is similar between a diesel ignition or spark ignition engine. It remains the same content. It will be function of combustion chamber design. About NOx, we can see that we produce more NOx with a spark ignition than with a diesel ignition itself. This is due to the fact that the temperature will be more homogeneous as we have a more homogeneous mixture. So the temperature will be higher. About N2O, it seems that in fact we have similar N2O content when we are around the occurrence ratio. And perhaps we have less N2O emissions when we ignite with decane. This has to be verified because N2O measurement is not so easy at the exhaust port as it is very small quantity. So anyway, if we put it in an equivalent of CO2 or global warming impact, in fact, it seems that finally diesel ignition is not worse than the spark ignition and ignition itself. So we have NO, N2O, NH3, H2. We have to find a strategy to mitigate, in fact, the pollutant. So there are some advertisements when they say, oh, no problem, SCR is available, EGR is available, we can do also catalyst and blah, blah, blah. It's not true from my point of view. SCR are not mature for ammonia engine, they are mature for diesel one. NOx divided by NH3 ratio is not constant, so perhaps we have to inject again ammonia. And also, we have to consider that there is a high percentage of amount of water in the exhaust gases until between 28 and 30%. What's about the catalyst efficiency? What's about life? So there are now new studies they start in order to see what's happened as function of the water content, as function of the ratio between NH3 and NOx, and as function of the ratio between NO2 and NOx. In ammonia combustion, there is no real problem with NO2. It's very, very small. So anyway, there is some technical challenge, but there are still some scientific challenge that we have to answer. Especially what's about the auto-ignition behavior of ammonia under elevated conditions and also with blends. We test 40 kinetics mechanisms, and some of them are perfect for pure ammonia, some of them are perfect with 5% of hydrogen, but they are not the same. What's about, in fact, the flame stretch injection behavior for pure ammonia on blends with ammonia? We still need to enhance the knowledge about the flame propagation, the effect of combustion promoter, the effect of turbulence, which is until now not well known and need to be investigated on model, and also the stretch effect. And sure, we have a lot of things still to do about the emissions. Chemical kinetics modeling, investigate on modeling low emission combustion mode like RCCI or RCCI. And so I didn't talk you today about the challenge to inject liquid ammonia spray, but there are some, not only due to the high latent heat of vaporization, but also due to the vapor saturator pressure trace pressure, where we have a strong flashballing process that can occur inside the injector vessel. This will change, in fact, the atomization mode, and this change also the predictability that we can have with classical atomization model. Thank you.